Okay, so this is the last chapter in the probability section, and it's about combinations and permutations. So what's the difference? So let's start with combinations. Combinations give you the number of ways in which you can select R elements from a set of N elements when the order does not matter. A prime example is the flower bouquet. So how many different possible drawings of size R, like the number of flowers in a bouquet, are possible from a set of N equals 10 items. So let's assume you go into a flower store and a flower shop and there are like 10 different flowers to choose from. How many different bouquets of 5 flowers can you make? And so here the order does not matter. We just ask how many ways are there of arranging 5 out of the 10. The formula is the formula for combinations, and it reads something like the number of combinations possible from a set of N when R elements are taken at the time. And I think the short version is like 10 choose 5 or so. But the formula is, so 10 choose 5, so we have a total of 10 flowers to choose from, and we want to make bouquets of 5. But then the formula is n factorial over r factorial times n minus r factorial. So how many possible 5 different flower bouquets can you generate from a flower store that offers 10 different kinds of flowers? And the answer is from 10 choose 5, so now it's 10 factorial. 10 factorial is 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, 1, over 5 times 4 times 3 times 2 times 1, and then again 10 minus 5 factorial again, 5, 4, 3, 2, 1. Okay, so then some things cancel out, like the 5, 4, 3, 2, 1 cancel out with those 5, 4, 3, 2, 1. And then we are left with 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2 times 1. And the answer would be 252 different kinds of flower bouquets. So typically, when you resort to Excel, you would use the formula for combin. It's equals combin. And then you see the same logic that we just went over is repeated here. So it says the number 10, number chosen 5, and we get 252. Okay, let's move next to permutations. And permutations give you the number of ways in which you can arrange R elements selected from a set of N elements when the order matters. And in this case, the prime example is the permutation log. So, but it's a specific permutation log. So, for example, think of it this way. So how many different possible drawings of size R are possible from a set of N items? The formula that gives you the answer is permutations, and it is very similar to combinations. So in combinations, we said from N choose R, and we said that is equal to N factorial over R factorial N minus R factorial. Well, for permutation, it's from N choose R. The numerator is the same, N factorial, but the denominator is just N minus R factorial. And this reads something like the number of permutations possible from a set of N when r elements are taken at the time. So how many possible 3-digit numbers can you generate from a permutation log? Well, the answer would be 10 factorial, which is again 10 times 9 times 8 times 7 and so on until you reach 1, over 10 minus 3 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, and then this cancels out, and then we will get 720. And I will say something about the permutation log in a second, but so in this case the formula is permut, and then it's again number 10, number chosen 3, and 720. Okay, so the combination log or permutation log is actually a little bit misleading, because what we assume with the permutations is that each number can only be chosen once. So normally when you have a log, let's say you go to the gym and you have a log on your in your locker door, well, the log could be theoretically 000, and in fact whenever you buy a log, the default setting is 000 and it will open. So that is technically not a permutation. So the permutation log that I was giving you was a true permutation log in the sense that the same number cannot repeat twice. So therefore there are only 720 permutations possible. But of course the log that you have and that has like 3 numbers that you can combine, that would be actually 10 times 10 times 10. So that would be 1,000. You would have 1,000 combinations. And those so this is not really a permutation log. So please remember that we assume for permutations that, and also for combinations, it's basically drawing without replacement. So for both combinations and permutation, it is drawing without replacement. So the only difference between combinations and permutations is that for permutations the order matters. Okay, so let's just take a look at another example. So let's say you have 5 Lego blocks and each in a different color. And so how many different combinations can you build? And so here, let's say if you have a tower, so we have like 3 blocks. So in this case, if we have, let's say, a block, let's say we have a tower which has a blue block and I don't know, a green one on top of it and an orange one on top of it. Well, that's the same combination as a block that looks like this. So that those are the same combinations. But those are 2 different permutations, because we have here blue, green, orange, and here we have orange, blue, green. So it's 2 different permutations, the same combination. So for combinations, the formula is 5 factorial, because we choose from 5, 3. So we choose 3 from 5, or from 5 choose 3. So it's 5 factorial, 5 times 4 times 3 times 2 times 1 over 3 factorial, 3 times 2 times 1 times 2 minus 1. 5 minus 3, 2 times 1. And then again some things cancel out. And then we have here 60 over 6, which is 10. For permutations, the order matters, and again, the formula is 5 factorial. Again, the numerator is the same, but then we don't also divide by r factorial, but only by n minus r factorial. So we have 5 times 4 times 3 times 2 times 1 over 2. In the numerator, we have 120 divided by 2, that's 60. So just to see again the difference in Excel. So we say combinations, it would be combin. From 5, choose 3. 10 permutations equals permut. From 5, choose 3. And of course we always have more permutations because the order matters. So here we have 60. Okay, so it's a relatively simple formula and Excel accommodates it nicely. So let's do another example, which is explaining the odds of winning the lottery. And here we have a lottery where you can win a jackpot if you get 5 numbers right out of 70. And then you also need to select a mega ball, which is a number between 1 and 24. Okay, so now earlier we talked about the multiplication rule. Here we need to apply the multiplication rule too. So if you take a look at the first odds, so this says basically those are the odds for what's the probability that you get 5 right out of 70, and again it's drawing without replacement, and you get that mega ball right, which is a number from 1 and 24. So we need definitely a multiplication rule. So the first question is, how many ways are there of drawing 5 balls from a bowl of 70? So we can put up Excel maybe here quickly. Okay, so what's the probability, or how many ways are there of drawing 5 balls out of 70? So that is combination, because the order doesn't matter. It's not like that you need to get a certain order of those balls. You just need to make sure they are the same that are being chosen as the winning numbers. So it's a combination, and we just say, okay, combin 70. So out of 70, choose 5. Okay, it's obviously a large number. Let's see if we can change the cell to a number. We don't need decimals then. Okay, maybe, and again. Okay, so it's 12,103,014 ways. Okay, so that means if these are the number of ways, the probability of just getting those 5 rights would be equal, but of course there will be lots of zeros, 1 over this. And now let's see. Okay, so that would be the probability, 0.7 zeros something. So it's easier to say 1 in 12 million. But here there is still, we also need to get that mega ball right, which is 1 out of 24. So here this is basically 5 out of 70. And how many ways are there to get 1 out of 24? Well, and there should be 24 ways. It could be the first or the second or the third or the fourth one right, but technically it is combin from 24, choose 1. It's 24. And the probability is equal to 1 over 24. Okay, so how many ways are there in total of winning? So that is 5 out of 7, and so 5 out of 70, and which is times 1 out of 24. Okay, so if you just multiply those, so now we get the 1 in 290,000 1,472,336. And I just spare you the probability. It has lots of zeros, obviously. We still can take a look maybe at the second, because this one says that you get 5, right? And you do not get the mega ball. Okay, so the 5 out of 7 is the same, but how many ways are there to get not the mega ball? So there are 23 out of 24 ways. So 23 out of 24. So what is the mega ball? There are like 23 ways. So that would be technically combin equal combin. So from 24, 23. So there are also 24 ways of not getting the Super Bowl. I did something wrong, hold on. So the probability of missing, actually, no, it's easier this way. So what's the probability that you miss the Super Bowl or the Mega Bowl? Well, that probability is probability miss Mega Ball. That probability is 23 over 24. Okay. And so it's a pretty high probability. So now we can also calculate what's the probability that you get 5 out of 7, or 70 I mean. So you get 5 out of 70 and miss Mega Ball. Yeah, that's a little bit more intuitive. Okay, so in terms of probability, I go now here. So in terms of probability, the probability of 5 out of 7, that is equal to 1 over 5 out of 7, and now times the probability that we miss the Mega Ball, which is, okay, of course still very unlikely, but if we add some decimal points, but now we need to get to the 1 in 12,629,232, well, the odds ratio is then the inverse of what we just calculated. So then we get, so we just did it from the probability side. What's the probability that you get 5 out of 70 and the probability that you miss the Super Bowl or the Mega Ball? And then we took the inverse or the reciprocal of it actually, so the 1 over the probability. And this is how we get the 12,629,232. Okay, so now you also know how to calculate the probability, and that concludes the chapter on probability or the lecture, but we still have a couple of problem sets, and yeah, I hope to see you there. So yeah, I hope that was useful.